this video, we're going to use the formal limit definition to prove the following limit. The limit as x approaches 4 of square root of x is equal to 2. Right, so let's write the definition first. Right, so if we show that this is true for this specific case, then that is showing us, proving that indeed the limit of this function as the x approaches 4 is indeed 2. So we're starting with this because we want to show delta value in terms of the epsilon value. So once we show the delta and then find what the delta could be in terms of epsilon, we'll install that then delta value into this somehow and get to that result, to the epsilon being greater than whatever is on the left side. All right. So our goal is to play around with the delta and find the possible epsilon value for that. The x minus 4 can be expressed as the product of the square root of x minus 2 and the square root of x plus 2. That gives you back this, if you multiply these two together, is less than that delta, right? So we just basically replace the left side of this inequality with that, with the product of these. But the problem is, you're thinking that you can replace this delta over square root of x plus 2 by the epsilon. That's not a good idea because the epsilon should be a constant, right? It should not be a variable, because if you involve a variable, that's not a good representation of the epsilon, right? So we can actually leap over this hurdle by understanding that this is indeed less than or equal to the delta divided by 2, right? Because the only way that this can be equal to the expression on the left side here is when the square root of x is 0. But when square root of x is not 0, it's positive, then you will have a bigger denominator than here. And the bigger denominator than here will make this fraction smaller than this fraction. Right? But this is a great idea to compare because now you can see delta divided by 2 is going to be a constant. There's no more variables there. Right? So you can go ahead and freely set this to the possible arbitrary value of the epsilon. I'm just replacing, notice I'm working with this part right here. I'm replacing this using this substitution so that we get to this. All right, so you can see that the delta is just replaced with a twice epsilon. That's what you see on the right side of that inequality. Remember that we showed that the product of these two, all right, two absolute values involving square root, but subtracting and adding, the product of this is equal to x minus 4 in the absolute value. Right, so that means if you set them equal, which they are equal, these two left sides, to solve for individual expression here, square root of x minus 2, you would have to divide both of these, if you set them to an equation, by this square root of x plus 2, right? And that's exactly what you see here. So square root of x minus 4 should be divided by the square root of x plus 2 in order to solve for the square root of x minus 2. All right? But the good news is that we know that the top can be manipulated, right? Because we know the top is less than the twice epsilon, right? So we know that this is going to be less than twice the epsilon over square root of x plus 2. That's going to be less than or equal to, now we're getting to this part right here. Notice that this is going to be used, okay? And also this substitution is going to be used. And why? Because the denominator here, right, this denominator was replaced with that denominator. And that's exactly what we did here. All right? So that's twice epsilon divided by 2, and that's less than that. And you know that because 2 over 2 is 1, so you know that's going to be 1 times epsilon, which is epsilon. So now look what happened. We showed that this side of this inequality is less than, here's your less than sign right there, the epsilon which you see right there, right? So we've successfully proved that this limit of the square root of x function as x approaches 4 is indeed 2. Thank you so much for watching. I hope this was fun and helpful. See you in my other videos.